Let me ask you something. You just opened this video. You typed a URL or maybe you clicked a link and within a fraction of a second this video started playing. But have you ever stopped and wondered what actually happened in that fraction of a second? Your device somehow figured out where this video lives on the internet. It created a connection to a server potentially thousands of kilometers away. It asked for data. The server responded. Packet of data travel through undersea cable, through router, through your ISP and reassembled into this video all in under a second. And here is the thing. If you want to design system that serve millions of users, you need to understand how this works. Not just at a surface level, you need to understand it the way a chef understands heat. Not just that the stove is on, but how it transforms ingredients. You should understand this. So today, we are going to break down exactly what happens when you type a URL and press enter. And I promise you, by the end of this session, you will never look at your browser the same way again. So let's get into it. So let's start with the analogy, the big picture, the restaurant analogy we will understand here. So before we dive into technical term, let me give you a mental model that will make everything click. Think of internet like a restaurant. You sitting at the table are the client. You are the customer. You have a need. You are hungry. In internet term, you are the browser or the app. The kitchen in the back, that's the server. It has all the ingredients, all the recipes, all the capability to prepare what you want. But you can't just walk into the kitchen and start cooking. There is a process. The waiter who takes your order and bring your food, that's the network. It carries your request to the kitchen and bring back the response. Now the menu. The thing that tells you what's available and how to ask for it. That's the protocol. HTTP is like a standard menu format. It defines how you make requests and what kind of response you can expect. And here is the crucial part. How does the waiter know which kitchen to go? Imagine there are thousands of kitchens in this city. Someone needs to look up the address of the right kitchen. That's the DNS, the domain name system. It's like the restaurant directory that converts a name, say Pizza Palace, into the actual street address. Keep this picture in your head. Every single concept we cover today maps back to this restaurant. I will keep connecting the dots as we go further. Alright, let's say you type www.youtube.com into your browser and press enter. Here is the fact that surprises most people. Your computer has absolutely no idea where YouTube is. It doesn't know the address. All it has is a human readable name. But computers don't communicate using names. They use IP addresses. Numbers like 142.250.190.46. So the very first thing that needs to happen is a translation name to number www.youtube.com to 142.250.190.46. And the system that does this translation, that's a DNS, the domain name system. Think of it as an internet phone book. So how DNS resolution works? So let's understand it step by step. Step 1 is your browser first check its own cache. Have I looked up this name recently? If yes, it already has an IP address in its cache. So it will mark it as done and no network call needed. Step 2. If the browser doesn't have it, it asks the operating system. Your OS has its own DNS cache. So OS also has a cache mechanism in it, right? So it looks up into the DNS cache. Now the step 3 is if the OS doesn't have it either, it sends the request to the DNS resolver. This is usually run by your ISP or a public service like Google. Google has 8.8.8 or Cloudflare which has 1.1.1.1. Next step is the resolver check its own cache. If it doesn't have the answer, it begins a journey through the DNS hierarchy. Next step 5 is the resolver ask a root name server. There are only 13 set of these in the entire world. So understand this, the entire DNS system is powered by only 13 set of servers. The root server doesn't know where youtube.com is, but it knows who handles .com domain. It says go ask the .com TLD server. So TLD stands for top level domain in this case. Okay. So step 6 is the resolver now asks the TLD server for .com. This server doesn't know the exact IP of youtube.com either, but it knows which authoritative name server is responsible for youtube.com. It says go ask Google name server. Step 7 is finally the resolver asks the authoritative name server for youtube.com. This server has a definitive answer. youtube.com is at 142.250.190.46, and the next step is the resolver caches this result and return it to your browser. Your browser now knows the IP address and your browser will also cache it. Your OS is also cache it. So all the middle hop will cache this result. So that's how you will get the IP address of youtube.com. So if I connect to our analogy, right, then consider it relates like this. You are in a new city looking for a specific restaurant. You ask a local, I don't know the restaurant, but I know the food district is on the main street. That is a root server. You go to the main street and ask again there. I don't know that exact restaurant, but Italian places are on block 5. That is TLD server. You go to block 5 and finally someone says, oh yes, it's a right. They're at a number 46. And that is an authoritative server in this case. So let's try to understand now why DNS matters for system design. Now, why does this matter for system design? There are 3 reasons for that. The first is DNS is the first thing that happens in every request. If DNS is slow, everything is slow. That's why DNS caching is critical. Second reason is DNS enables load balancing. A single domain name can map to multiple IP addresses. youtube.com might resolve to different server depending on where you are in the world. This is how companies serves billions of users globally. Third reason is DNS enables failover. If one server goes down, DNS can redirect traffic to healthy server. It's a fundamental building block of reliability. So the key takeaway here is DNS translates human readable domain names to IP addresses through a hierarchical caching system. It's a starting point of every internet request and critical lever for performance, load distribution and reliability. Now next interesting thing is consider your browser has the IP address. It knows where the server is now. But knowing someone's address isn't enough, right? You need to establish a connection to that server. You need a rules of communication. That's where TCP IP comes in. TCP IP is actually 2 protocols working together. They form the foundation of how data moves across the internet. Let's start with IP. The internet protocol handles addressing and routing. It's like the postal system. Every device on the internet has an IP address, and IP's job is to make sure data packets get from the source address to the destination address. But here is the thing about IP. It's unreliable by design. It's like sending a postcard. You drop it in the mailbox and hope it arrives. There is no confirmation. Packets can get lost, arrive out of order, or get duplicated. IP doesn't care about this. Its only job is to try to deliver the packet. So IP here is like a postal service. It knows addresses and tries to deliver your package, but it doesn't guarantee delivery, doesn't track the order of packages, and won't tell you if something got lost. This is where the TCP comes in. TCP sits on the top of IP and adds reliability into it. It guarantees that data arrives completely in the right order without errors. How? How this is possible? Through something beautifully called as a three-way handshake. Three-way handshake add reliability into it actually. So before any data is exchanged, the client and server do this. Step 1 is sync. The client send a sync packet to the server. This is like saying, hey, I would like to talk. Are you available now? Step 2 is sync acknowledgement. The server receives it and responds with sync acknowledgement. This means, yes, I am available and I acknowledge your request. And the step 3 is acknowledge. The client sends back an acknowledgement and great, I acknowledge your acknowledgement. Let's go and talk now. Only after this three-step dance is the connection established. Now data can flow reliably. It's simple like you dial a number which is sync here. The person picks up and say hello. That is a sync acknowledgement. You say hi, it's me. That is again an acknowledgement from the sender side. Now you can have a conversation. Neither side starts talking until both sides confirm they can hear each other. Now, in this context, you might hear about UDP, that is User Datagram Protocol. Unlike TCP, UDP doesn't do the handshake. It just fires data and hope for the best. So handshake mechanism is missing in UDP. So definitely the reliability is missing in UDP. So why would anyone use UDP then? It is because of the speed. When you are a video calling on Zoom or playing an online game, you would rather have a tiny glitch than wait for a network to resend a lost packet. One slightly corrupted frame is better than a frozen screen. So in UDP, even if you miss some packet, even you miss a frame in your video, it's fine for you, right? So that if that is the use case, then people will go for UDP. In system design, TCP IP matters because every choice has a trade-off. When you design a chat application, you want TCP because messages must arrive and in order. When you design a live video streaming system, you might use UDP because speed matters more than perfection. And in interviews, when you talk about latency, throughput, connection pooling, all of it goes back to TCP IP. Remember this. This is the plumbing. So the key takeaway from this is IP handle addressing and routing. TCP adds reliability through three-way handshake, guaranteeing order and complete delivery. UDP trades reliability for speed. In UDP, reliability is not there. The choice between TCP and UDP is one of your first system design decision. Now next concept which we should understand is HTTP. That is a language of web. We have a connection. Now the TCP handshake is done. Now the client and server needs a shared language, a set of rules for how to ask for things and how to respond. That language is HTTP, that is Hypertext Transfer Protocol. Back to our restaurant analogy, TCP established that you are seated and the waiter is ready. Now HTTP is the menu. It defines what you can order, get, post, put, delete, and how the kitchen responds. 200, okay, 404, not found, 500, kitchen error. So this is how the analogy relates to HTTP. Now how an HTTP request work? An HTTP request has a few key parts. The method tells the server what you want to do. Get means gives me data. Post means here is some data. Please process it. Put means update this. Delete means remove this. The URL is the specific resource you are requesting, like /video/trending on YouTube. The headers carry metadata. Who you are, what format you accept, authentication tokens and cookies, and the body, which is optional, carries data you are sending. Like when you submit a login form, you send the data, right? That data will go as a body. When the server receives your request, it sends back the status code. These codes tells you what happened, and here is a simple way to remember them. So 2xx, this series means success. Here is your food, enjoy. 3xx means redirect. That dish moved to new branch. Let me redirect you there. 4xx means client error. You ordered something that doesn't exist or you are not allowed in the VIP area. That is 403. So 5xx series of errors means server error. Our kitchen is on fire. So our kitchen is not working. So this is a 500 error. Here is a pro tip that interviewer love. Whenever you design a system, think about what status code your API should return. A well-designed API uses the right status code. 201 for created, 204 for no content, 429 for rate limiting. These details show maturity in interview. Now here is a problem with HTTP because everything has a problem, right? So HTTP also has problem. Everything is sent in a plain text. If someone intercepts the communication between you and the server, they can read everything. Your passwords, your messages, your credit card numbers, everything. That's terrifying, right? So HTTPS solves this by adding TLS, Transport Layer Security. TLS encrypts the communication so that even if someone intercepts the data, they see nothing but a scrambled gibberish. So HTTPS is like a sealed envelope. HTTP is like sending a postcard. Anyone who handles it can read it easily. HTTPS is like putting your message in a sealed envelope. The postal workers can carry it, but they can't read what's inside. So how TLS works? So TLS handshake happens right after the TCP handshake. Before any HTTP data is sent, first the client says hello and tells the server that encryption method it supports. The server responds with its SSL certificate, which contains its public key. This certificate is like an ID card. It proves the server is who it claims to be. The client verifies the certificate with a trusted certificate authority. If it checks out, they agree on a shared encryption key. From this point on, all communication is encrypted. Even if someone is eavesdropping or intercepting your messages, they can't read anything. And here is why this matters for system design. HTTPS adds latency. The TLS handshake takes time. When you are designing for performance, you will think about things like TLS, session resumption, HTTP/2 multiplexing and certificate pinning. These are optimization that reduce the cost of encryption. So now let's zoom out and see the complete picture. The client-server model is the fundamental architecture pattern of the internet. One side asks, the other side answers. The client is anything that makes requests, your browser, your mobile app, a smart TV, even another server. The server is anything that processes that request and sends back a response, a web server, a API server, a database server. So anything that send response is a server. Let's trace the complete journey one more time quickly. So you type youtube.com. Your browser calls DNS to translate the name to an IP address. Your browser uses that IP address to initiate a TCP connection with the three-way handshake. If it's HTTPS, and it's always should be, a TLS handshake encrypts the connection. Next is your browser sends an HTTP GET request for the home page. YouTube server processes the request, fetches the data and sends back an HTTP response with HTML, CSS, JavaScript and API data. And the next step is your browser renders the page, or it renders all HTML, CSS and you see the YouTube home page. All of that under 1 second. That's the engineering marvel that we take for granted every single day. In system design interviews, you will constantly be working with this model, client-server model. When someone asks you to design Twitter or Uber, you are essentially deciding what does the client send, what does the server do, how do they communicate, where is the data stored, how do you handle millions of these requests simultaneously. Everything we cover in this series, load balancing, caching, databases, message queues, it's all plugs into this client-server model. It's all start from here. So this is the essential part to understand in the system design. So the key takeaway is every system you will ever design follows the client-server model. The client requests, the server respond, DNS resolve addresses, TCP ensure reliable connection, TLS adds security, HTTP define the conversation rules or format. This is the foundation everything else built upon.